Krishna, how about job for you? Oh no, it's all right. Because I have to go down there and you have to open the door for the door. No, it's all right. Thanks. Yeah, I was gonna ask you to go down and go down and join the Zoom meeting for me down there. But I have to go because you don't have the door code. I said, you're a good guy. Morning, morning. Wait, which channel is that you man? Good man, good, good. Super busy. Super busy. Go upstairs, put my lunch in the fridge, then after work downstairs. Upstairs, going upstairs. The most challenging class I ever taught. Two locations at the same time. All right, welcome everybody. Okay, so we have a hiccup. All right, everybody, please turn off your audio if you have joined. If you joined, please turn off your audio. Oh, maybe it's the audio right there.
I'm muted. Oh my God. Wait. Oh, no. Wait. Okay. Yes. Check if you can hear me now. Yeah, I just realized I was muted both places. Check it again for me. You were trying to tell me. Now I have an echo. Testing. All right. Testing. All right.
All right, can you guys downstairs hear me? Dinesh, you can hear me downstairs? All right, thanks so much. Manish, thanks for coming up and telling me. Sorry about it. Okay, so what I was saying to these people upstairs, right, is that Monday's class is inspiration for doing the individual paper / case study, right? This is the inspiration for the paper / case study. All right. So a couple things. Let me reiterate a couple things. So first of all, we're going to use the same Zoom link for the rest of the semester, right? It's a recording meeting. I created a recording meeting. And by the way, let me just throw in a super duper quick thing here, which is that you gotta work hard while you're young. Don't wait until you're my age to start working hard. The whole semester. You know what I've been doing for the whole semester? I've been disconnecting the PC equipment so that I could attach my laptop to the projector in the labs. All I had to do was run a Zoom session on the PC in the lab, right? You lose that mental agility as you age. You lose that ability to just kind of see obvious things very, very quickly, right? Anyway, so same Zoom meeting, right? Work hard while you're young. I was also telling Leading Innovation 3 weeks ago that careers are going to be shorter and shorter because kids are coming up right now. For example, who know deep learning. There's teenagers who can create a deep learning model. I'm not joking enough. I was at a science fair 2 Fridays ago, and there was a kid who created a deep learning model I think it was to predict some disease thing. Anyway, all right. So we're in March 26th, and the two assignments which have been extended are extended to March 28th. So that's 2 days more, right? Point number 5 or 6, might have been 4, is that Monday's class is inspiration for the case study, right? Because one of the things that this class should teach you is that there are multiple opportunities for deep learning, and you should be seeing a deep learning / MIS opportunity every minute of the day, right? I was talking about a Pepsi bottle, how in the future, based on Moore's law, right? And I'm about to show you a 1956 hard drive to show that it will happen, right? Because when I talk about the technology that's going to be inside of a Pepsi bottle in 20 years, it's going to sound like $200 worth of technology. But in 20 years, that technology will cost 3 cents, right? We're talking about the Pepsi bottle and how you will have many you're gonna have many different sensors inside of the Pepsi bottle. It's gonna be it's gonna have a gyrometer, which is the thing you have inside your phone, which enables the look. All right, so you have two things in your phone. You have a GPS tracker. That's gonna be in the Pepsi bottle, so it's gonna know where you bought it, where you moved to, and where the bottle started and where it ended, right? It's also gonna help with sustainability, right? The issue of sustainability, recycling of plastics, yeah, right? But the GPS tracker in the Pepsi bottle is gonna show the behavioral patterns while drinking Pepsi. Because in order to stay ahead of Coca-Cola, they will have to go deeper and deeper and deeper, more precise, more accurate, more intense, more comprehensive, more complete analysis of Pepsi drinking behaviors, right? So you're gonna have a gyrometer. You're gonna have a GPS. I was explaining to the class up here that the gyrometer is the thing inside your phone that tells whether it's upright, flat, tilted, right, etc., right, and how it's moving, right. And I was saying to them that when you enable location on your phone, you're actually allowing them to see all different kinds of things, whether you're using the phone while you're upright, whether you're walking, whether you're distracted because you're tilting the phone up and down, right? 10 years ago, it was a big deal when there's this new feature. There's this new feature where they introduce this new feature where when you tilt the phone, the screen goes off. When you tilt it back up, the screen goes on, right? That's a battery saving feature, right? So you're gonna have a thermometer in the Pepsi bottle. You're gonna have a gyrometer. You're gonna have a GPS tracker. You're gonna have biosensors that measure bio stuff, right? You're gonna have a flow rate meter, right? So for example, it's gonna test your enzymes in the mouth, right? It's gonna have a flow rate meter to see how fast you drink it, when you drink it, time between sips, all of that, right? All inside of a Pepsi bottle. People, it's coming. The question is, are you gonna ride that wave? Are you gonna watch the wave go by? Or is the wave gonna, is it gonna be a tsunami that floods you, that that floods over you, right? There's waves in life, and it's your choice how you deal with that wave. I'm trying to prepare you to ride that wave, to surf that wave. Let's look at a 1956 hard drive. Let's look at that hard drive in 1956, right? This is what it looked like. 1956, 5 megabyte hard drive. Okay, now you guys can't see anything, okay? Can you guys downstairs see this? Can you guys downstairs see this? Can you see this downstairs? Where's the chat? Where's the chat? Okay, very good. All right. So it took 5 men to push a 1956 5 megabyte hard drive, right? Up into a truck, right? Now, do you understand why those 10 different sensors that I told you will fit inside of a Pepsi bottle and cost 3 cents? Do you see why now? Do you now see why? You have to see the future, people. You can't let the future happen to you. You have to see it. And you have to ride the wave. And if you're smart, you make it happen. You're one of the people who make those sensors and put those sensors into the Pepsi bottle and use those sensors and analyze the data from those sensors. Yeah? Right? So in other words, remember, okay, so you have that 1956 hard drive, right? Which is 70 years ago. right? And now this is what a hard drive inside 1 GB hard drive inside smartphone, right? What does it look like, right? 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 So, all right. This is what a 1 GB SanDisk SD card looks like, right? In fun, right? That's 1 GB. Sorry. Sorry, 1 TB. 1 TB micro SD disk. So this 1 TB micro SD disk is going to be 200 times, 200,000 times what this hard drive is. You see what's happening here? So this thing, right? Right? This thing is not, this is a couple grams, you know, it's 5 grams. It's 5 grams, right? You know how much this is? If 5 men are pushing and pulling it, then it's 500 pounds, right? All right, so let's do some math here, people. Let's do some math here. So we have 5 grams, right, versus 500 pounds. Right? That's 227,000, right? So 5 grams. So you have the IBM, this SanDisk. You have IBM, right? All right, cool. 5 grams versus 227,000 grams, right? All right, SanDisk is 1,000 megabytes, right? And this is grams, right? Very cool. So 1,000 megabytes, and then this IBM is 5, right? It's literally flipping. You see what's going on here? It's literally inverted. So in other words, let's calculate megabytes per gram, right? Megabytes per gram. So this is equal to that divided by that, right? 5 megabytes. That's not megabytes per gram. Okay, all right, very cool. Let's do the same over here. Megabytes per gram, right? So 45,400 megabytes per gram versus 0.000005 megabytes per gram. All right, now let's calculate the ratio, which is equal to that divided by that. All right. So what we're saying is that the information density of this SanDisk drive, right? The information density of this SanDisk drive, right? This versus this, right? Is the information density is 9 billion times. 9 billion times. There's 9 billion times more information on this little drive than on this drive. So what's going to happen in another 10 years, 20 years? In another 20 years, that 1 terabyte will fit on DNA, on a single strand of DNA. Right? Right? They're going to store data on DNA, right? Right? Storing movies on DNA. I saw a thing one time, right? All right. So they stored a short movie in the DNA of bacteria. So if you know anything about biology, you know that basically DNA is microscopic. You need a microscope, right? Right? All right. All right. Let's move on. So when I tell you that information, we'll be measuring data. We'll be measuring data from every possible source in the future. I'm not joking. All right. This is the last theory class. What we're going to do after this is we're going to work on a project. Next week, we'll start working on the project exclusively. We're going to come to class, work on a project. Right? All right, very cool. So let's look at some advanced techniques for improving your deep learning model. Yeah? All right. Now, I've shown you some basic techniques, but there are some other techniques, right? So we'll look at what's called callbacks. Callbacks is a way to, sorry, retrieve the information. Yeah, absolutely, right? So with a callback, we can see what's happening inside the loop. It's a feedback loop. It's what we call a feedback loop, right? Where basically the model can change what it's doing depending on the results that it's achieving. Yeah. There's also what's called batch normalization. Yeah. We looked at normalization, where essentially what we did was with normalization, we put everything on the bell curve and we created z-scores for our data. Yeah. And by doing what we call that scaling, by scaling the data, we can achieve better results because we put all of the data on the same scale. Yeah. So for example, you have a credit score of 650. You have a salary of 60,000 or 80,000, right? You have a day of the week, 1 to 7. You put all of that on the same scale by putting it on, by giving everything a z-score, yeah? Which is negative 3.16 to 3.16, right? You basically put it down the bell curve where 0 is average, negative 3.16 is 3.16 standard deviations to the left, right? And then 3.16 deviations, standard deviations to the right is, like the maximum, yeah? All right. We already mentioned dropout, which helps you to avoid overfitting, yeah? Dropout is a way where basically we turn off the neurons. And by doing so, we effectively avoid overfitting. Then we have what's called learning rate scheduling. Learning rate scheduling allows you to control the learning rate more precisely. So that we talked about learning rate and the fact that if you keep the learning rate the same, then it's kind of like running into a brick wall without stopping. Yeah. More realistically, it's like you're going up to a stoplight, and instead of stopping at the stoplight, you're overshooting the stoplight. You want to stop at the stoplight, right? And this is why accidents happen. For example, people see the yellow, they think I can make it. Then they see the red. They say, oh, I can't make it. I have to stop. By the time they see the red, it's too late to start stopping, right? With learning rate scheduling, it's a way of slowing down the learning. Remember, we're doing gradient descent, right? So we're coming down the gradient. I have to apply the brakes as you're coming down the gradient, right? Otherwise, you're going to overshoot the bottom. Remember, we have the gradient. All right, remember we have the gradient, all right? Remember you have the gradient, and you want to stop at the bottom of the gradient, yeah? Because at the bottom of the gradient, where you have the minimal what? Start with L. Where you have the minimum, start with L, loss, right? And minimum loss typically corresponds with the highest accuracy, but not always. You have to be very careful, right? But you have to start slowing down before you actually hit the bottom. You have to start slowing down on the hill itself. Otherwise, you're gonna overshoot and go over to the other side, right? All right. Then there's what's called early stopping, meaning once you see that so for example, you're keeping track of your training accuracy, which is how well the model fits the data. But you're also at the same time keeping track of your validation accuracy, right? Which is how well the model fits the test data, right? So the training accuracy is how well the model fits training data. The validation accuracy is how well it fits the validation data, right? Or the test data. Because understand something, in almost every situation, you will achieve 100, you can easily achieve 100% training accuracy, right? It was very difficult to achieve high accuracy on on-scene data that the model has not been trained on, yeah? So early stopping is similar to dropout in the sense that it prevents overfitting by stopping before you overfit the data to the training data, right? Right? You know, again, it's kind of like when you study for an exam, like when you study for an exam, you study how to work a math problem, a simultaneous equation, for example. 3 apples plus 2 oranges equals $5. 8 oranges plus 5 apples equals $10, right? How much does an apple cost? How much does an orange cost? Now, if you swap that particular equation over and over and over and over, you'll be able to work it in like 5 seconds. Yeah. But if somebody else says no, okay, now you have 15 apples and 3 pears. And that's worth $12. Now you have 8 pears and 2 oranges, and that's worth $15, right? You can't work that problem because your mind has been so intensely focused and trained on this particular problem you practiced on. Your mind is unable to transfer over to on-scene problems, right? This is the problem of overfitting. Overfitting is like making a glove for David Simmons' hand. So the particular ratio of, so the specific ratios of thumb to blah, to blah, to blah are perfectly fit. But when you put it on somebody else's hand, it fits very badly. What you have to do is create a glove that's just generally fits a thumb, generally fits a right? It fits the general proportions, right? Underfitting is like you have a mitt, right? You just have this big mitt, right? And it just fits your hand down. Anybody ever seen a mitten? A mitten or like if you, or like, oh, well, or like a cricket glove. You know, those cricket gloves, they just have these massive fingers. Yeah, it can fit everybody, right? But it doesn't fit anybody really well. That's underfitting, right? All right. Then you have gradient clipping, right? And then you have also transfer learning, right? And we'll see how these work. All right. Callback. What are callbacks? Functions executed during training at specific points, right? You have early stopping, model checkpoint, reduce learning rate on plateau, and you have TensorBoard, right? All right. So early stopping, like we said, what it does is when it starts to overfit the model, it stops the training, right? Because at some point, what it's gonna do is it's gonna start to fit that training data super, super well, but it stops fitting unseen data well, right? Model checkpoint. What model checkpoint does, for example, is it saves the model. All right, so normally you would only save the model at the end of training, right? You'd save the model at the end of training. But what you find sometimes, especially towards the end of the training, is if you overtrain it, right? And especially if you haven't adjusted if you don't have learning rate scheduling, then the accuracy starts to fall, right? The accuracy starts to fall because you pass the low point of the valley, right? So you have gradient descent. And basically what happens is that if you don't slow down, then you're going to pass this point, which is the lowest point, where the loss is lowest. Yeah. Remember, loss starts high, and you train on the model until it gets to the lowest point. Yeah. Now, if you don't stop it soon enough, then it goes back up the other side of the valley. Yeah. And then the accuracy starts to fall again. Yeah. Actually starts to fall again. Or sometimes what you find, for example, is that it starts to, I mean, it won't really per se. Okay, so that's not totally accurate. So what actually is going to happen is that it's going to start to bounce back and forth. Yeah, it's going to start to bounce back and forth. Yeah, it's not just going to simply climb up the wall again. That's not never going to happen. That's a lie, right? So what's really going to happen is that, oops, yeah, so what's really going to happen is that when it goes up here, it's going to go back up here, right? And it's going to start bouncing around, right? Right? It's going to start bouncing around. It's really what's going to happen. Yeah? It's going to start bouncing around. So what model checkpoint does is it saves the model every so many epochs, right? Remember, this is, each time the arrow bounces is an epoch. Yeah? So like I say, if you don't start to slow down, right? You don't start to slow down, then it starts to bounce around at the low, around this point. Now, we'll talk about bouncing around here. Normally, we're talking about like you might get, like it might be 88% here, 90%. Um, etc., right? So this might be like 88%, 90%, etc., etc. So you're gonna find that the accuracy is going up and down, essentially. Yeah. Now what you can do is save the model checkpoints. Yeah. By saving the model checkpoints, for example, you can save the model when it's at its best. Yeah, you can save it when it's at its best. So you save these 5 model checkpoints, right? And even though the accuracy has reduced again, let's say at epoch 12, you're at 90%, and at epoch 14, you get back to 88%. Because you've saved the model at epoch 12 with 90%, you have that model, you can still use that model. Yeah. Because the problem is that when you rewrite, okay, so you have something like this. You have something like this, right? Epoch, and then you have accuracy, right? Epoch and accuracy, right? So you have at epoch 12, you have accuracy of 88%. Right? At 13 goes to 90. At 14 goes to 90, 91, right? At 15 goes to 90. At 16, it goes to 88. 17 goes back to 91, right? 18 goes back to 90, right? At 19 goes back to 88, and at 20 goes back to 91, right? So that's the situation you're looking at when you have it bouncing around like this, yeah? Right? So it looks like this on the gradient descent curve, essentially, yeah? Now, if you see with model checkpointing, what you can do is save this model, right? You can save this model because if you rerun the model, bad news for you. Okay, so this time you say, okay, I'm going to rerun the model, but I'm going to run, instead of 20 epochs, I'm going to run it for 17. So guess what happens to you the next time? Guess what happens to you next time? Epoch 12, yeah, are 86 this time, 13, 86.5, right? Right? 14, 89, 15, 91, right? Right? See where this is going? And the whole thing just gets shifted up on it. 16, 90, 17, 89, 18, 88, 19, 87, 90 again, right? But remember, you basically had shut it down here, right? Oops. Yeah. Yeah, shut it down after 17 epochs. So you still don't end up with the best model, right? So model checkpointing allows you to save the model after each epoch, pretty much, or after a certain number of epochs. Yeah, that's what model checkpointing does. All right. All right. Reduce learning rate on plateau. Reduce learning rate on plateau. It does a similar thing. So basically, what it does is, no, if you are slowing down the learning rate, you're slowing down the learning rate. If you're slowing down the learning rate, then it will look like this. You have this big learning rate, smaller, 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 right? You're screeching the brakes right until it hits the bottom of the valley, right? So you find that by the time you get here, if it looks like this, and you're slowing down the learning rate, then your curve will look like this, right? Then your thing will look like this, right? It will look like let's do it over. Then it will look like this. It will look like 1286, 1387. I said 12, 80, 13, 85, 14, 87, 15. No, let's put the 20 bucks, right? 87, 88.5. Right? 89, 90, 90.5. Yeah. All right, good. So, yeah, so what I'm saying is that you end up with a kind of plateau, right? Notice that what happens with the accuracy is that it plateaus. Okay, anybody knows what a plateau is? No, because you skipped geography class. This is what a plateau is. A plateau is a hill with a flat top. Top of the hill is flat. It's a hill with a flat top. Yeah. Grand Canyon has a lot of them, right? But this is not really this is not what I learned about plateaus in geography. It wasn't. This is a cliff. A proper plateau, right? It's gonna look more something like it curves up and then it flats. Yeah. Yeah, pretty much, right? It slopes up and then it flattens. Yeah. So with learning rate plateau, what it does is it plateaus into the maximum learning, into the maximum accuracy, right? So by the time you get, by the time it hits the maximum accuracy, the learning rate starts to drop off rapidly because it senses that the callback sees that you've achieved the maximum learning rate. And so instead of allowing it to bounce back and forth, yeah. So instead of allowing it to bounce back and forth, right? It flips the learning rate smaller and smaller so that it plateaus, yeah? So that's what happens here. It looks more like this. You have a nice flat learning rate, yeah? And so the curve looks something more like, instead of it bouncing back and forth, right? Going up and down, you get a nice smooth curve that has a flat top, yeah? All right. Okay. What is the way? Oh, okay. All right, cool. All right. And we'll look at TensorBoard and all of that. Okay. It's an example of a Keras callback, right? All right. So early stop in patience equals 5. What it means is basically if you don't see the accuracy changing after 5 epochs, go ahead and stop. Yeah, this is essentially what it means, right? And it says take a model checkpoint. In other words, save the model once it starts to do that. Yeah. Batch normalization. So what it does is, all right. So remember when we run our code, when we run our code, let's go back to our code over here. We'll run our code. Oh, and by the way, yeah, so you get the checkpoints inside this folder here. For example, we create model checkpoints inside the folder, right? All right, very cool. So when we run the code, notice we had a batch size, right? We said the batch size equals 32. Yeah. Remember, what's happening is that it's putting that many records on the GPU and it's processing them in parallel. Yeah. And because it's processing them in parallel, it speeds up the processing, right? Now, remember, the larger the size of the GPU memory is, the more batches you can put on it. Oh, that's like yeah. So the more batches you put on the thing is the more batches you put on the GPU is the faster it trains, right? But now instead of simply normalizing the values across one record, you're normalizing the values across the whole batch. Yeah. And that again speeds up training and aids with convergence, right? Helps the model to train faster, right? We look at that more, right? All right, let's look at dropout. Like we said, and we covered dropout before, it disables neurons during training, yeah? And so basically what we said is that it turns off the neurons, right? And that prevents overfitting. Because what's happening is that the network is no longer learning all different types of features which only apply to the training data. Yeah. We'll look at that in we looked at that in we looked at that in module. Looked at this at it in this little thing, right? So we have the neurons in the layers, and what we do is we turn off neurons, right? Because of that, it's no longer transmitting the data to the neurons that it would normally be connected to. Yeah. And that prevents overfitting. All right. Learning rate scheduling, right? So fixed learning rate isn't always optimal. It's actually never optimal. Actually never optimal. So there's a couple ways you can change the learning rate, right? And one general way is what they call decay. Yeah. Decay meaning now the term decay comes from the idea of half-life. So with nuclear material has what they call half-life, right? So the half-life of nuclear material, of nuclear waste. So what happens with half-life is that let's talk about half-life. No, I don't want to talk about half-life. It's kind of an unpleasant thing. Bottom line though is that if we have nuclear war, then what's going to happen is that it's going to take hundreds of years for the Earth to be inhabitable again, right? So lesson of the day, don't get into a nuclear war, right? Because the whole Earth will be uninhabitable for hundreds of years, right? All right, but the idea is that nuclear material has what they call half-life, right? And You know, I don't really remember about nuclear physics that well. But the idea is that the idea of half-life, the concept of half-life is that every time something happens, it halves itself, right? It's kind of like when you have a memory. Every time you remember something about an event, you remember half of what you remember the last time. Yeah? Anyway, bottom line is, with decay, you're reducing the learning rate, right? With each epoch. Yeah? And there's two big ways. There's what we call step decay, and then there's exponential decay. So what does step decay look like? Step decay looks something like this. Yeah? You have the learning rate, right? You have the epoch, and you have the learning rate, right? And let's say in epoch 1, you start with a learning rate of 5e minus 5, right? So what's 5e minus 5? That is 5 exponent 5, right? Meaning 5 times 10 to the minus 5. To the minus 5, right? Or 5 over 10, well, 100,000, right? You guys remember your scientific math? 5 times 10 is 5 times 10 to the 1, right? 10 to the 1, right? Let's do this in work. Do this over in work. Right? So 5e minus 5, as you will probably see in the code, right? Let's say the code says 5e minus 5, right? I want you to understand what these numbers are. Right? 5.0 e to the minus 5. What is this? 5 exponent minus 5, right? It's 5 times 10 to the minus 5. 5 times 10 to the minus 5, right? That's one way of saying it. In fractions, it's 5 over a 1 with 5 zeros behind it, right? And to understand it, what we're saying is, so exponent means times 10. So exponent of our number is that number is 10 to the power of that number. Yep. What was it? So exponent of a number is 10 to the power of that number, right? Right? So exponent 5, so exponent 5 is 10 to the 5 power, right? equal to 10. Let's put a 5 here. Let's put it. No. Right? 10 to the 5th power. Right? So exponent 5. 10 to the 5th power. Right? Equals 10 to the 5. Right? Exponent 3 is 10 to the 1. Third. Yeah. Equals 10 to the 3. Right? There's a, let's rationalize. Rashmita will always participate. Let me tell you something. This young lady is gonna go far, she's gonna go high, and she's gonna go for a long time. Brave, bold, enthusiastic, eager, energetic. That's Rashmita Moore. People, you gotta speak up. That's the business you're in. When you sign up for a master's program, you sign up to be the leaders in organizations. You're not signing up to be shy and afraid to speak up. All right, good. Then to the 3rd, right? Good. And it looks like this, right? And it looks like this, right? A 10, a 1 with 5 zeros, right? Right? Equal to those, right? Exponent, let's flip it. Exponent minus 3 is 10 to the minus 3rd power. So the negative 3rd power is 10 to the minus 3. Yeah, 1 by 1,000, correct. Yeah. Right? Is 1 over 1,000. Right? This is worth 5 minutes of the class because deep learning, fine-tuning a deep learning model is all about learning rates. All about learning rates at the end of the day. And this is how you're going to see learning rates being expressed, right? Right? So similarly, exponent minus 4 is 10 to the minus 4th power. Was 10 to the minus 4 equal 1 over a 1 with 4 zeros, right? Let's make this more complete. E5 equals right? Right? E minus 3, E minus 4, right? Right? So you have to understand. You have to understand what these things look like, right? So let's look back at our learning rate over here, by the way. And what does learning rate mean? Can anybody remind me what learning rate means? What am I looking for? You gotta work hard while you work. The brain don't stay sharp forever. All right, and here it says 0.0005, right? But it could have also said you could have also seen this said as 5e minus 4, right? In other words, 5 over 1, 2, 3, 4, right? That's the other way of putting it, by the way, right? That's the other way of putting it. Right? Sorry? Yeah, right. Totally right. Yeah, totally right. Okay, right. So that means that so the 5e minus 4 is 5 exponent 4 minus 4. 5 times 10 to the minus 4th power plus 5 times 10 to the 4 equals 5 over 1000 equals 0.0005. That rounds up the discussion, right, of exponents. Hmm? Hmm? Right? All right, very important. This is really where the rubber meets, where the rubber meets the road. All right. All right. Step decay. So step decay you might go from 0.0005, 0.0004, 45, 0.0004, 0.00035, 0.0003, right? Or in other words, 5e minus 4 5e minus 4, 4.5e minus 4, 4e minus 4, 3.5e minus 4, right? 3e minus 4. Each time you're reducing it by a fixed size, right? This is step decay. Right? With exponential decay, you have what they call a gamma. So for example, you might have a gamma of 0.95. They start with 5e minus 4, right? That's equal to the gamma 0.95 times that, right? Or let's say it's 0.9, right? The 0.9 brings you, the first time it brings you to 4.5e minus 4. But what happens when you bring it down is it starts to drop off less dramatically. Yeah. So goes to 4.5e minus 4, and 4.05e minus 4, 3.65, 3.28, etc., etc. But exponential gamma 0.9, right? But let's do it with a gamma of 0.8, and let's see what happens, right? We have that. Actually, we'll change it to 0.8, and then we'll bring it down, right? It drops off extremely rapidly, right? Yeah. You can choose the gamma. You can choose the rate at which it falls out, the exponential. I mean, you can choose a step and you can choose the gamma. The other thing with step decay is that normally you can choose after how many steps. So you can say after 3 epochs, or after 5 epochs, or after each epoch, right? And all of this is stuff you have to kind of experiment with before you really get it right. Early stopping, like we said, early stopping prevents overfitting, right? So in other words, if you find that your accuracy looks like this, epoch accuracy 12, 13, let's say you have a nice plateau, 0.87, 0.89, 0.90, 0.90, etc., right? So after the 17th epoch, you're definitely wasting time. Yeah. So early stopping can say, okay, once you get to the plateau, just stop. Yeah. Gradient clipping. Let's skip that for now. Transfer learning is essentially where you use pre-trained models. Yeah. You get a model that somebody else trained, and you simply add the last layer, or you add 2 more layers, right? Now, with transfer learning, what you're basically doing is the model that they've already trained has learned the big features or the major features. So, for example, let's say you train a model on detecting dogs versus cats, right? You can then take that model and use it and train it to detect wolves versus lions, yeah, by simply adding a few more layers, right? So you take off the last layers of the model. Now, the thing with okay, no, let's not say wolves versus lions. Let's say you have a model, airplanes versus ships, right? Military airplanes versus military ships, yeah? You now want to detect civilian airplanes versus civilian ships, yeah? Right? It already knows what a ship looks like at a fundamental level. It knows the basic shapes of a ship, right? In the first few layers of the model, right? It knows what a wing looks like. It knows what a propeller looks like. It knows what a jet looks like. It knows what the tail of a plane looks like, right? So then all you have to do now is add a few more layers for the civilian aircraft and retrain it, right? And so essentially what you've done is you capitalize on the knowledge already captured in that earlier model, yeah, which already knows what a basic ship looks like versus what a basic airplane looks like, right? And then you just add a few more layers, right? So you freeze the base layers and fine tune the top layers, right? The base layers already know ship versus airplane, right? The top layers will be what a civilian ship looks like versus a civilian airplane, right? All right, let's call it that for today. Okay. Maybe just data augmentation. Data augmentation is basically you can do things like zoom in, you can center the image, right? You can zoom up the image, You can rotate the image, right? You can add noise to the image. You can add, you can recolor the image, this kind of stuff. And what that does is it adds more training data. Yeah. So for example, let's say you have a data set of plant disease and it's images taken during the day. Yeah. Images during the day, taken during the day. You may not be able to detect plant disease at night with that model. So what do? You take the photos and you darken them, reduce the light in the images. Yeah. Now, having reduced the light in the images, it knows what the image of a plant looks like at night. Yeah. And then you can train it and you will have better results on detecting plant disease at that from pictures taken at night. Make sense? So you can use these kind of data augmentation techniques, which essentially is adding more data to the training data, right? To make it more real world. Yeah. So like I said, rotating an image. Say for example, you have pictures of cats standing up, where you want to be able to see a picture of a cat lying down, or you only have pictures of cats, um, um, you know, from a certain angle. Well, you can rotate the cat in some of the pictures, right? So now we can detect pictures of cats from different angles, right? All right, let's call it that today. Let's see who is here today. But yeah, so the point though, people, is, oh my God, we're what time? Sorry about that. The point is that you must see opportunities for deep learning every minute of your life, right? Every minute of your life, you should see opportunities for deep learning, right? And for MIS implementation in general, right? Because what's going to happen is that technology is going to get dirt cheap, super, super, super dirt cheap, right? It's going to get cheaper and cheaper. People are going to be measuring more and more information constantly. And, you want to write that way. All right. Sorry to the people downstairs. I'm coming right down. Do not move. I'm coming down there. All right. Priyanka, Bharat, Heyman, Ajay. Okay. Wrong class. All right. Let's try the second. Sanjay, Sai Prasad, Carla, Sai Krishna, Moriani. Moving fast enough. Vamshi, Deep Chandu, Satya, Devika, Rohit, Yamini, Manikanta, Harif, Govardhan, Virbudulo, Venkat, Siva, Shafi, Rashmita, Rama, Lavanya, Saimani, Sai Gopi, Ashwin, Bali, Bala, Jaideep, Bhagavat, Banu Prakash, Darius, Aditya, Nishant, Soumya, Navyasri, Navina, Sridhaka, Srikurti,
Hey, sir.
Shashank, I heard it's over. Oh, Sridhaka, Shreddy, Prashant. All right, see you guys. Have a great weekend.
I was here, sir. all of us select one place and record 5 minutes video, or is it fine if we have clips of 5 people, like 5 people recording videos?
All right, you know what? Ideally, you should have it, but yeah, you could try. Yeah, but yeah, you could.
And when you say a folder with the following model training notebook, then you mean the folder in Jupyter notebook?
Sorry, I mean the folder.
In the Jupyter notebook? Or like just a folder which contains.
Yeah, it should contain the
these
Jupyter
files?
notebook.
Okay.
Dr. Simmons? Can you hear me?